This will be basically an introduction to image processing and also a summary of some developments in the area, some classical, some a bit more traditional. Okay, I'll start off with an introduction to the area. After that, I'll touch up on something called new sensors. By sensors, I mean sensors in the field of imaging. That is, some new models for cameras, some mathematical models and related areas. Then I'll discuss something about image transforms. Then I'll touch up on image enhancement and restoration. After that, something on feature detection, that is trying to detect features automatically from images. Then reconstruction from projections, a little bit into that. A little bit on image morphing. Then I'll touch up a bit on motion analysis. The penultimate topic that I'll touch upon is image-based rendering, which is the last topic that I'll touch upon is something that's rather current, that is trying to detect hoaxes in images and videos, which is a rather current topic. We'll start off with a historical motivation for the entire subject of image processing. So, well, it's not really asking for the moon, but the area started off with something to do with the moon. In the year 1968, would you remember there was a pretty important event that took place in the year 1968, which really gave a big impetus to this area on image processing. Because image processing as an area of research has been around since quite some time, since the early 60s also. But would anybody remember? Let's try to keep this talk interactive. Unlike what I said, right? I cannot face up to my wife and things are not very interactive. I have to more unidirectional here. So let's be interactive at least. Could you remember an incident that took place in the year 1968, or you would have definitely heard about it, which has something to do with image processing and the moon? Yeah, there was a mission to the moon, absolutely, ma'am, you're right. Apollo 8. Apollo 8 went to the far side of the moon. Because normally the way that the moon rotates and the way that the earth rotates, we only see one face of the moon, almost, at all times. Now, before Apollo 11, they say landed on the moon in 1969. In 1968, Apollo 8 went to the far side of the moon, and for the first time, pictures were beamed down to the earth of some part of the moon that we have never seen before. And it so happened that these images were not very proper. They were corrupted by noise. There were some deformities in them. And for the first time in front of the world media, image processing techniques were used on those pictures that were beamed down from Apollo 8. And the results of image processing techniques were there for the world to see. So this was the first time that in the press, the results of image processing techniques had come out. So more or less, interest in the area started off then as a global phenomenon. Now let's come to what an image is. Now the way I'd like to start is with this little sukti. Ekam sad vipra bahudha vadante. Ek satya ko buddhiman log anek tarikon se dekhte hain. One truth is interpreted by the wise in many different ways. Now it couldn't be too apt with regard to images as well. Now all of you, at least most of you, how many of you are teachers? All are teachers, okay. So you wouldn't really mind me going to the board and then start scribbling in possibly an indecipherable script on it, right? Because yeah, if we are all teachers, then we have a weakness, right? The moment we see a whiteboard or a blackboard, we just tend to go towards it and for no rhyme or reason start scribbling on it, right? So I'll try to do that. Yeah, is this the eraser? Yeah, because otherwise, no, I hope to use this eraser. I remember a couple of my teachers who didn't like to erase the board. They used to just find every available place. Okay, the world around us is analog. The world around us is analog, but then why at all do we go in for the digital world? And what do we do in going to the digital world? The idea is basically, if this is what electrical engineers call a signal, the idea is basically to have a function of an independent variable, some sort of independent variable, which could be time, typically for signal processing applications, and for images, obviously it is space. Now the idea is that to go from the analog world, the world around us is analog, to go from the analog world to the digital world, what we are doing is we are taking snapshots of the analog world at, for example, if it is a one-dimensional signal, at different points in time. We are basically taking snapshots of the analog world, and we are doing a quantization in two dimensions, in two axes. One is along the independent variable. We are also quantizing our values along the other axis, which is that of the dependent variable. And if we represent these using bits, we get a digital representation of a function or a signal. Now, why at all do we want to do so? But before that, we are engineers. So, we'd also like to know what we are losing out and what we stand to gain out of this. For example, there is a very important theorem which is called the sampling theorem, which is something that all of you might be aware of. The idea is that Shannon, in his 1930s theory of communication, gave the sampling theorem as something that allows us to reconstruct the analog world or the original analog signal perfectly from a digital set of outputs or from a discrete set of samples. Alright? And what Shannon said was that if the original signal is band limited, I'll come to this pretty soon. If it is limited in terms of its frequency content, then it is possible to reconstruct it uniquely without any error if we sample the waveform at something that is slightly more than twice the maximum frequency content. So that is something that most of us know and understand. But before, what is frequency and why at all do electrical engineers have such a fascination for things like time, space and frequency? I'll also come to that. So in a way, fine, there is some theory that tells us that we can do lots of nice things even if we don't have a very large set of values or an infinite set of values. That's the idea. Okay, that is what I have in these slides as well. So it's basically for an image. Different people look at images in many different ways. People in signal processing would interpret images as signals. Alright? Two-dimensional signals. People in mathematics are also interested in images. They would look at images as being matrices or arrays, two-dimensional arrays. Each of these arrays taking on a particular value. There's a two-dimensional matrix, each of these takes on a value, and we represent something as being proportional to a brightness value. So 0 would be something very dark or black, and white would be 255, for instance. There could be color images. Color, as we know, is basically a set of three frames, like a red, a green and a blue. So the set of the three would make a color image. And yes, mathematicians are interested, statisticians are interested, because there can be a lot of random field modeling, for example, for images. Then lots of people are interested in images. I'll talk about it at the end of the lecture also. It's become a completely interdisciplinary field. And anything that has things to do with algorithms, people in computer science should naturally be interested. Okay, so this is basically what I talked about. So if I have an analog waveform out here, I can discretize it both in terms of the independent variable as well as the dependent variable. So if, for example, I quantize the dependent variable in three levels, okay, 0, 127 and 255. So this is one possible representation of a function or a signal. Okay. No, that's fine. I'm more comfortable with using this. Okay. So I have another alternate representation wherein this particular function or a signal, I can represent it with each value being proportional to an intensity. So something that's 0, I can represent using black. Something that's 255, I can use white for that, and something that's somewhere in between 127, I can use gray. So this basically is an image representation of the signal. This is one way to look at an image or a signal in one dimension. So what is it in terms of two dimensions? In terms of two dimensions here, just as in terms of one dimension, I had one independent variable out here and I had a function of that independent variable along the y-axis. In this case, I can take the independent variable not to be time, as in the case of an audio signal, but to be space. Okay, so something that's varying with x and something that's varying with y. And I have a function of that along the z-axis. So I'll have a function of x and y. Okay, so something that's varying with space in this direction as well as in this direction, and the height would be that value of the function. Alright? And in this case, I'll go back to my slide. So this, for example, in the following manner also. So if I have a 0 value out here, this could be dark, and if I have a 255 out here, so this would be white. Okay, and something in between could be gray, for instance. So this is basically the concept of an image. Alright, I have a function of two variables out here, and this is what I have in terms of an image. What is a video? In a video, basically I have a set of images that have been grabbed across time. So in this case, there is a third axis as well. There is a temporal variation also. So there is not just a variation in the intensity or the color, which is across space, x and y. There is also variation with time. Alright? And note a couple of things. For instance, alright, I'll come to that when I come to compression and related matters. But this is the idea. This is basically what images are. This is basically what video is. And I'll introduce the concept of frequency. What does one mean by frequency? The best way possibly to explain frequency is to look at maybe something like a sine wave. Alright? Maybe if this is 0, I'll maybe start from here. Then in that case I can represent maybe a function of time as a, let's say, sine omega t plus phi. Now in this case, a would be the amplitude of the sine wave. Let's see what are the parameters. Then phi would be the phase, that is from where exactly am I starting the sine wave. And the important thing is here, this is the omega parameter. Omega I can represent as 2 pi. Omega is an angular frequency. So this I can convert to a linear frequency using this very popular relationship which we have all suffered through in school. So this I can write as 2 pi divided by a time period. So this is basically the concept of a frequency. The concept of a frequency is basically something that's repeating. Something that's repeating has a frequency connotation. Something that's repeating in time. For example, most musical signals tend to repeat in time. There is a harmonic structure to that. Right? Something that repeats in time, so there is a concept of frequency. Something that changes very slowly, we'll say has less frequency, right? Rather than something that changes very rapidly. So we'll say that this is a high frequency signal or a high frequency waveform. This is a low frequency waveform. Right? This is basically the concept of frequency. Frequency has got something to do with the repetition. Okay? Alright. Now we'll come to a couple of terms that you would have heard. They sound similar and have rather similar connotations. At one end, I have a two-dimensional image or a set of two-dimensional images, and in this case, on the other hand, I have three-dimensional data. Right? Now, if from three-dimensional data I get either one or more realistic 2D images, this is basically computer graphics. Right? Using two eyes. Basically what one has is our two eyes basically serve as two cameras out here. I have a left camera and I have a right camera out here. Okay, we are all familiar with camera models, right? 6th standard, all of us have gone through things like this. If I have an object and if I have a lens, right, then any ray that's parallel to the principal axis will appear to go through a point which is called the focus, and any ray that goes through the optical center goes undeviated and we get an image. So this is a model of a lens. There is a similar model for a pinhole camera, right? This is a model for a pinhole camera wherein I have an object here, and if I have this sort of an arrangement, then I get an image out here. Okay, so they are basically equivalent, and a pinhole camera is the mathematical model that covers all of these situations. Now the idea is, for instance, if I have two cameras out here, these are the image planes. I have the optical centers of the two cameras here, and suppose there is an object in the world. So how is an image of that object formed? We basically join these with the optical center and the point where it cuts the image plane, that is the image of the object, right? Similar thing happens here. Now, the interesting thing is, suppose we look at it the other way around. Suppose we had these two images and we knew that these were the images of this 3D point, okay? Now, what our brain does for us is, it basically joins the optical center of each of our two cameras with that point and projects it in the world, and wherever they meet, that gives us a perception of depth. For instance, our most common perception of depth is using binocular vision. Of course, there are other cues also for depths. So this is the idea. So just as human vision is there, so computer vision also aims to do similar things with semantic. Basically, we are trying to get some semantic information out of the images. That is computer vision. And image processing. In image processing, basically the input is a two-dimensional image and the output is another two-dimensional image. Basically, without taking any semantic information out of this. And what is pattern recognition? Pattern recognition is a much more general topic wherein there are lots of techniques, statistical, syntactical, and whatnot, and to try to do something with it, right? So these are how these terms are related to each other. But nowadays, in today's world, these cannot be divided into watertight compartments. There's a lot of commonality between them. Okay? There are places where all of these three would overlap, and the penultimate part of my talk, which is image-based rendering, I'll come to some of these things. Intermixture of computer graphics, computer vision, and image processing. And I'll talk about some movies as well, wherein techniques from all three domains have been used. Okay, this is basically the model of the camera that we are all familiar with. This is basically what I drew out there on the board, right? Something that we are familiar from our 6th standard onwards. Now I'll come to that. Now any imaging in any part of the electromagnetic spectrum actually turns out that it follows similar laws. And from the point of view of imaging, we'll be concerned with cameras. A camera is our basic sensor. Now whether that camera is a one-dimensional camera, for instance any scanner or any photocopy machine has a one-dimensional camera, a flat bed camera that just goes forward and back. That's a camera. Then of course we have our familiar two-dimensional cameras that most of us have used. And there are three-dimensional imaging cameras as well, laser range imaging, wherein in addition to the other things, one gets a notion of a depth as well. So all of these are cameras. And we are going to talk about cameras and things to do with cameras for most part of today's talk. Now, this part of my talk concerns new sensors. By sensors we mean optical sensors or cameras. Now obviously there must be some disadvantages of existing sensors or existing cameras. Now I would like to motivate this with a couple of examples. Suppose there is a group of people who are getting together after a long time, and what do you want to do? You want to capture this on film, capture this on a camera. Now what we generally do is we make people stand beside each other in a group, and then we get them to take a group photograph, right? So this tells you a slight disadvantage of an existing camera, because every camera's field of view is limited, right? If there is a large group of people who are assembled, one beside the other, the cameraman has to go back, right? You have to go back because the field of view is very limited. So that is one restriction of existing cameras, that is a limited field of view. Then you might say, well, if the field of view is limited, so what? I at least have the image. But then you will remember that if I take an image from a distance, okay, I lose clarity, I lose resolution, right? Because I am taking things from a distance. And another thing that you'll recognize is the fact that every camera has a limited range for the corresponding lens position, if you have control over the lens, wherein objects of interest will be focused, okay, properly focused. Things which are closer will not be focused, things which are far away will not be focused. That's something we have all experienced, because if in any formal gathering a cameraman asks us to stand in a row, then he'll make us stand close to each other. He won't say that, okay, you stand behind him by, let's say, a couple of feet. No, he'll try to get us all together in a group, because every camera has a very limited range within which the focusing can be done, or with regard to the lens setting. Alright? And well, our filmmakers seem to use this, typically in the Saas Bahu serials, right? When the Saas is standing right behind the Bahu, at one point in time, the camera focuses on the foreground, right, the Bahu, and after some time, focus changes onto the Saas. It's used as a cinematographic technique, but then this is a limitation of cameras, right? It would be wonderful if every pixel in every image would be equally focused. How about that? So, there are lots of disadvantages of existing sensors. So basically, why do we want to go in for new sensors? Yeah, this is the reason. You want more out of existing sensors. And I'm going to discuss 4 things. One is super resolution. Alright, getting images that are at a higher resolution than what we have, and some techniques to do with that. First thing, I'll deal with the super resolution. Then mosaics, that is stitching together images. I'll motivate each of these with a couple of examples. Then a camera that has a 360-degree field of view. All of us are teachers, we love to have such cameras in classrooms, for instance. You har taraf dekhiye, aage piche, upar niche, har taraf, right? And the other thing is, without doing too many nasty things to the camera itself. How nice would it be if you could apply some algorithms on the images themselves and then get so much out of it. Then another variant is, how nice would it be to have an image where every pixel is properly focused. It's possible. All of these are some fairly recent developments, 1990s developments, wherein all of these, it's possible to do these with minimum amount of effort. Alright, so I'll just discuss these. I'd like to take an example here. Now the first thing that I'd like to specify here is, this is in conjunction with the concept of frequency. What does frequency have for an image? We can understand what frequency is for a one-dimensional signal. What does frequency mean for an image? An image has basically 2 independent variables, which is space, x and y. Right? So what is the interpretation of frequency for an image? What does it mean when one uses the term frequency? By frequency, one basically refers to variation in the intensity, for instance. Suppose we are looking at grayscale images. How does intensity vary with space, with x and y coordinates? So if intensity does not vary much, we'll say that it has a lot of low frequency component. Right? If the intensity does not change too much with space, that is, for instance, regions with constant intensity or near constant intensity, and regions wherein the gray levels change drastically, with space that has high frequency components. So this is the concept of frequency. Okay. Now the concept of super resolution is interesting. So I'll motivate this with an example here. Okay, this is an image of a shoe. This is better. Now, if I want to say that, okay, I want an image of double the size. Alright, now what is the first thing that comes to your mind? Maybe every pixel I'll duplicate it in 4 locations. Alright, 4 locations around it, and I'll get something like this. This is the first thing that comes to one's mind. But then one also realizes that, hey, I haven't added any new information to this. And the picture would appear pixelated. Okay, there would be a blockiness because every intensity value is getting duplicated at 4 locations. Right? So there's a blockiness in terms of that. You're all familiar with pixelations, right? Sometimes we see videos of people maybe who want their identities protected. So around their faces we see pixelated effects. That's it. Okay? So you might say that fine, most of us are electrical engineers, we know what to do with these, we'll smooth out the image. Or what electrical engineers call low pass filter. We'll come to that. As has been done here. Well, this image is smooth. But how nice would it be to have a super resolved image? I'll motivate this with this particular example. Look here. In this case, you can see that the overall image is much sharper, right? It's much sharper, and you can also see the seams on the shoe, right? This is a super resolved image. This is an image of double the size, double the dimensions, and a super resolved one versus one that is simply blown up and smoothed out. Okay, you can also tell that this would not be my shoe, for instance. Otherwise, you won't be able to see too many stitches on my shoe, and plus it won't be so clean either. Okay, so I'll just basically explain, I'll give you an idea about the problem, what it means mathematically, and why it's such a difficult problem after all. For example, it would be very nice if a high-flying aircraft or some satellite could take images of the very friendly country that we have to our west, and then suddenly we want to get more details of some part of those images. Alright, so I'll motivate this with a one-dimensional example. The idea is the following. Now, suppose we are given an image or a signal of a particular size. Okay, let's say this is the signal or the image that's given to us. Now, I want an image or signal that is of double the size. So basically, for all of these sampling positions, okay, I want to put in one more sampling position in between every existing sampling positions. So here, I have a blank position here. After that, I have a filled up one here. I have a blank one here. I have a filled up one here again. I have a blank one, a filled up one here, blank one, and a filled up one over here. Okay? So do you get the problem? Just as for an image. So I am just taking the one-dimensional counterpart to be able to explain this topic better. What I'd like to do is I want to fill in the blanks. I want to get an image or a signal which is of double the size. So basically I want to find out what is here. Okay? I have a couple of choices. One choice that's immediately obvious is basically what came to our mind when one wanted an image of double the size. Whatever is the value, whatever is the value here, I simply duplicate it here. Okay? Whatever was here, I simply duplicate it here. Okay, but the first thing you notice is the pixelation effect. Say, okay, maybe I smooth it out or I apply a low pass filter, but we are not putting in any extra information. That's also something that one has to recognize. You might say, well, I might like to do something better. What I'll do is a linear interpolation. What does a linear interpolation mean? I'll basically join two of these points with a line. Okay? I'll join two of these points with a line and I'll take this. This is much smoother than before. But again, as you can see, this is dependent on the two adjacent values. This is not adding any new information to it. Okay, those in communication would call this a zero order hold. Alright, it's basically the previous sample you are holding it. This is called a zero order hold. What is this called? This is called a first order hold, because first order why this is a line. But still you will recognize while this is smoother than before, this does not introduce any new information into it. So, how can I pose the problem? The problem I can pose as follows. And why at all are these solutions slightly unrealistic? Can you give me a physical significance? Why don't these fairly simple techniques work towards getting super resolution? What is it that we are missing out on?
Change in the degree of density of the...
Exactly, that's the answer. The change that's actually happening. Okay, now maybe can you put it a bit more mathematically? As an electrical engineer, your answer is absolutely right. We want to capture the change as it happened. Alright? So who is the culprit here? The culprit is basically our sampling. The degree to which we are sampling in space. Right? Because the original image or the original signal could be something like this. Okay? And because of the sampling process, right? Because of the sampling process, we have sampled it at different points in space. Now what we need to estimate is what the original signal had been at this point. And what we are given is absolutely nothing. We have to estimate the original signal. And as you can see, this particular problem would have infinite solutions, because through these 2 points, I can fit an infinite number of curves, and out of which exactly one of them was the original curve. So this tells you that the problem is not too easy. So typically what one does is, one tries to put these in a constraint. You're all familiar with well-posed problems, right? How do you define well-posed problems? Well-posed problems mathematically are those which, for one, have a solution. Second, the solution is unique. And the third criterion is, mathematically, the solution varies continuously with the data. What does that mean? Suppose I have an independent variable x, right? And I have y equal to a function of x. Then, for a well-posed solution, if I vary x by a small amount, x plus delta x, and if I look at the variation in the dependent variable, which is a function of the independent variable, then I must be able to bound delta y by some amount. If delta x is bounded, then delta y also should be bounded. So these are well-posed problems. Now this is not a well-posed problem, typically. So what one does is one typically puts these in a constraint optimization framework, and by putting in further constraints, one tries to find solutions that satisfy those constraints. Okay? So this tells you that the problem of super resolution is not too easy. And this is still an area of research. There are quite a few existing techniques, okay, which, for instance, have been used to generate these images. And this basically is an overview of the problem, okay, which is a pretty difficult problem, but there have been possible solutions. Another problem here is mosaics. It would be nice if I could take a camera into a large gathering. Remember that example that I had taken of a large number of people standing in a group? It would be nice if I could take a camera, take different snaps of the groups, right, at different positions, from different positions, and then stitch the images together. Okay. It would be nice if you could do that, but however, This in general is not possible. Okay, all of you who would have done a course in engineering drawing might have experienced this. How many of us have copied engineering drawing sheets? I shouldn't be asking teachers, but let's raise our hands. I have also done it, so I can raise my hand safely. Alright, see, it's not easy. First thing, how does one copy an engineering drawing sheet? How would you have done it? If you had done it, yeah? Topo method, what is it? Yeah, generally in scientific terms, it's basically having an optically true slab of glass and having a monochromatic source of light underneath and then projecting a sheet onto this. Now this is one way of doing it, right? And this is one way of doing it without understanding too much about the original. The other way to do it is possibly to put in an honest effort, and after that, if I have a reference sheet, I take it to a photocopy machine, I take a couple of photocopies, and after that, what do? I take a pair of scissors and a tube of glue, and then orient those sheets, have some things in common with them. See, because typically engineering drawing sheets are quite large, right? What do you call it? A0 size or whatever? I've forgotten that. So, and after that, the idea is to basically get two sheets which have some amount of overlap, orient them and paste them together. How many of us have done that? No? I have done it and I can tell you that it doesn't work. Why? The reason to that is exactly the reason why mosaics are not defined for a general case. Any idea why? Why it's not possible to get very good alignment? Sheets tend to curl, right? So there is a three-dimensional effect. Sheets are never perfectly plane, and sometimes photocopy machines just might go up and differences in depth. Okay, so getting alignments is very difficult. This also tells you why the problem of mosaicing is not defined for the general case. Okay, so here I will give an example. However, there are some specific cases for which mosaicing is a solved problem. Okay. This is an image of the blackboard, and this basically satisfies the conditions in mosaicing. First, that you cannot get the image of a blackboard in one frame. Right? So basically what I have done is, this is my horrid handwriting. I basically went to the blackboard and took many images of the blackboard, okay, from various orientations. I did not constrain myself. Some of them had me looking at the blackboard like this, in some cases like this. You can see they have been taken from various angles, right? Is that clear? And after that, it's easy to show that for a planar structure like a blackboard, the problem of mosaicing is absolutely well defined. You can stitch these images together, and it can be shown that any two of these images are related by a 3x3 non-singular matrix called a homomorphism. Okay, this can be proved pretty easily, and this is a well-known result. And after that, what did I do when I wanted to see these images stitched together? I'm a teacher, right? So I gave an assignment. Okay, I never do things myself, I get things. It's also called, this is one of the most fundamental laws of physics, right? Law of conservation of energy. Lazy, we don't do stuff ourselves. So this, for example, you can see is an assignment, the result of an assignment, and this alignment is reasonably good except for some parts here, for example. But then it can be shown that if one knows feature points accurately to a sub-pixel level, it's possible to do this with very little error. What problems do you note with this? आपको क्या ऐसा लगता है जो उतना अच्छा नहीं है, जो आपको भी लगता है कुछ कृत्रिम है, which looks slightly artificial? What is it that looks a bit odd? The points where they have been joined. Yeah. Why does this occur? Intensity difference, exactly. Why does that intensity difference happen? Our cameras, most of our cameras are equipped with a feature which is actually a disadvantage in this case when one wants to stitch together images. Any idea what this is called? It's called automatic gain control. Alright? And it's especially there in digital cameras. For instance, if you take a digital camera to a ill-lit environment, if it's quite dark, after some time you'll find the camera, after a couple of seconds, you'll find the camera adapting itself to the dark environment. And still things appear to be imageable. On the other hand, if you take a camera suddenly to a very bright environment, let's say bright sunlight, initially everything will appear white. After that, it is gradually stabilized to just a couple of fraction of a second, it will stabilize to something that can be erased. This is called automatic gain control, wherein very dark or very bright environments get somewhat equalized. This is exactly.
As we are entering in the cinema hall, at that time also.
That, sir, I think the point that you make is our eyes also do automatic gain control, which is absolutely correct. Our eyes also automatically do this automatic gain control. So cameras try to be a bit more general, bit more natural like us. That's a very nice point. Yes. But for this particular problem, it's not nice because you see these seams out here. You'd like to work seamlessly, literally as well as figuratively. So can you give a couple of heuristics that will get rid of these seams? Some heuristic that you might like to point out? See, these heuristics sometimes don't work, but in many cases they do. And that's just about the best that one can do. Any guesses? What might you like to do to remove these seams? Yeah? Come on, it can be a non-technical answer as well. Maybe you could answer that, well, I'll take it in Photoshop and maybe airbrushing option and then do something here.
Removing the frequency.
That's exactly it. So technically it amounts to removing the high frequency component out from here. So what you're doing is you will be doing some amount of low pass filtering on the edge. That's exactly the answer. That's exactly what you do in Photoshop. Pick up the airbrushing option and maybe smooth it out. Right, this is called image smoothing. Yeah, exactly. You can do that. There are some other things also you could do. For the parts that are overlapping, you could maybe take information from either one of the images wherein there is this overlap, which might give rise to the seams, or take an average. Take an average of both the places where it's coming from, right? So a simple bilinear interpolation. Sometimes that works. Also something you could do is you could normalize the images with regard to the means and the variances. You could normalize the images to have zero mean and unit variance, and after that stretch it back to the original range. All of your teachers, you would have done this. Typically first year labs. First year labs cannot be taken by one person alone, right? First year electrical engineering or programming labs. What you do is typically many different faculty members take that. And every faculty member has got his or her own biases, like maybe some teacher is known as a lenient teacher and somebody is known as to be a strict grader. What do you do when you want to equalize the marks? You would all be doing it in your educational institutions. You would first take the mean of each individual teacher's class, okay? Then make the means overall to zero, okay? Zero normalize the means, or subtract the means from the marks. That way, overall, it would have a zero mean. Then you can combine them. That's the idea, to get things on different platforms onto a common platform. You would make them zero mean. You could also equalize the variances. Let's say if a faculty member is very lenient, then he or she would mostly put marks towards the top. What you want to do is you want to stretch the range. So you normalize everything to have a unit variance. After that, you know the max and the min. Then you stretch everything to that. That's exactly what you can do with colors and variables. Okay, these heuristics work quite well. And in fact, nowadays there are some digital cameras which have the panorama mode. You might have seen panoramic images. They do this image blending reasonably well. They also use these heuristics. There's no magic in what they do. Some other examples. This is the Powai Lake. I used to be at IIT Bombay before, and this is what one person did out there. I hope not while the class was going on. Okay, so these images were taken, and after that, The person stitched them together. As you can see, this is relatively free of seams and other distortions. You can find a couple of distortions here and there, but overall the effect is pretty nice. It's not just that, but it can also be shown that if you have a camera which is rotated about its optical center, then all of these images would be related by this 3x3 non-singular matrix called a. Okay, it's possible to do this here as well. We are talking about mosaics, and this is what another problem in mosaics, that is, suppose, fine, we have some theory which will enable us to take images in certain circumstances and then stitch them together. But what happens if it is motion? Then in that case, we'd like to estimate motion, remove the motion, and then stitch them together. I'll talk about some things regarding motion analysis tomorrow. As for now, you can see a panoramic mosaic that's being done step by step. This is basically the Student Activity Center at IIT Bombay. And ये curfew वाला situation इसलिए दिख रहा है because we've removed the motion. Okay, otherwise it's a pretty populated area, especially during office hours, right? When one is supposed to be in classes. And this is another example of a mosaic. This is in the Computer Science and Engineering Department of IIT Delhi, the General Computing Lab. Okay, now I'll talk about omnidirectional sensors. This is basically the 360-degree field of view camera that I was talking about. The first thing that is interesting is the fact that panoramic sensors are not omnidirectional sensors. Fine, you can take a panorama, you can put a camera on a tripod, rotate it about its optical center, stitch the images together, and then get a view, get a wider field of view. Alright, but still that's not an omnidirectional sensor. Why? We'll talk about this. Another requirement here is that we need perspective projection. Why? Because that's the way we view the world. Alright? Perspective projection, something that we're all familiar with. And basically we can apply standard image processing and computer vision algorithms on images which are perspectively realistic. Yeah, that's consistent with our view of the world, and we can use standard algorithms on those images. Now I'll give a step-by-step motivation behind the Omnicam. An Omnicam is basically an omnidirectional camera, something that you can see all around. This is an ordinary camera with a very limited field of view. So one of the things that possibly could be done to increase the field of view is that one could have the camera placed at different locations and one could try stitching the images together. However, we just talked about this. This is not possible in the general case. In some cases, yes. For example, when a camera is rotated about its optical center, alright, we can stitch them together. But the first thing is that this camera cannot look all around. Because why? There is a mechanical movement that's associated with rotating the camera, and obviously it cannot be done in real time. No way. Real time is at least 25 frames per second. That is, you have 40 milliseconds to process each frame. You can't do that with a mechanical arrangement. One way out is something called a fish-eye lens. You would have seen images taken by a fish-eye lens. Typically they appear in newspapers around about some important events. Like Republic Day or Independence Day, there's an image taken by a fish-eye lens. For example, in front of the Red Fort, there's a person going. So typically fish-eye lenses, the images have nearly a 180-degree field of view, a hemispherical field of view. But there are two reasons why one would not like to go in for a fish-eye lens. Any guesses? First is images are distorted. They are non-linearly distorted. Alright? Things which are at the center of the image are least distorted, but towards the edges they appear to be curved. Okay? Typically you would have seen images that appear to be curved around the edges. They are taken with a fisheye lens, although they have nearly a hemispherical field of view. So that's one reason. Okay? These distortions are non-linear and not very easy to remove. Any idea about the second? Why might you not like to use fisheye lenses? It's this. They're hard in the pocket. They're very, very costly. Alright? Now, a very easy and a low cost solution is something that's called a catadioptric arrangement. That is basically having a combination of a mirror and a lens. Lens in a camera and a mirror. We're all familiar with this. The use of a mirror to get a wider field of view. Every one of us who drives to work would know this. A rear view mirror, it has a wider field of view. Combine that with a camera. Now, how can we combine this in a way to get a completely 360-degree field of view? That's interesting. Actually, the interesting part is if you go back into history, Maharaj Ashok ke darbar mein bhi tha. He had a spherical mirror on the ceiling. Okay, and he used to use the human visual system to look up at that and find out what was going on in the court, or rather what was not going on, whatever. That way he had a hemispherical view of things. But there's one thing, everything is distorted. Spherical mirror would give a distorted image. But the idea is to have a wider field of view. That is perfectly satisfying. Okay, now with this in mind, the problem is posed as follows. Suppose I have a ray coming in from a direction theta. Okay, and this I am looking at a small cross section of a mirror. A small mirror, a cross section of it, and here, and this is the depth. So what I want to find out is what will be the cross section of this mirror, which obviously has to be a curved mirror because we want a wider field of view. What will be the shape of the cross section such that we'll get a 180-degree field of view, for instance, a hemispherical field of view. Now this turns out, in fact this is something interesting, most of the fundamental problems, some of them at least, have a very easy solution. The solution to this is, believe it or not, this is a first order differential equation, and the solution to this is quite unsurprisingly paraboloid. It can be shown, this is just high school math. It can be shown that with a paraboloid one can achieve a hemispherical field of view. So the solution to this would be a parabola. This is a parabola, right? And after that, make this a solid of rotation. Rotate that parabola about its central axis and you will get a parabola. So unsurprisingly, something that will give a 180-degree field of view is a parabola. So this is an example of a omnicam. A camera that has a hemispherical field of view. This camera is looking at a small paraboloidal mirror out here, and I'll show a couple of images taken with this, in fact a couple of videos. And how does one get a complete 360-degree field of view? By placing two of these back to back. It's a very simple idea. It's a very, very simple idea, and yet it's pretty profound. Okay, and this is not very costly either. Just a common off-the-shelf camera. This is something called a telecentric lens. Telecentric lenses don't cost too much. It's basically a good approximation to an orthographic field of view, and placing two of these back to back. And this has got a plethora of applications. So I have a couple of videos out here. This, for example, is what the camera sees. This is in an omnicam arrangement. This is the small paraboloidal mirror, the shiny part, and you can see a blind spot. This is basically where the camera looks at itself. That's it. Apart from that, it can see all around. Okay? And this particular application is video conferencing. You have exactly one camera, but you can have any number of virtual cameras, just given by a simple closed form mathematical formula. You can create any number of virtual cameras and create perspective projection images which are not distorted. It's possible to undo this distortion using a very simple closed form formula. Obviously this is going to be distorted, but the distortion you can get rid of using a closed form formula. And all of this is in mid-90s hardware. Okay? And all of this is in real time. You can put any number of virtual cameras anywhere. Just a program, piece of software. Just put in parameters and it's going to give you a virtual camera. Or wherever you want, with just one actual camera. So video conferencing is one application. Another application is, yeah, you guessed right, navigation. Our perception of depth is with two cameras here. Alright? So what about having any number of virtual cameras? One can look all around and also get depth. In navigation, that's an important problem, right? Obstacle avoidance. So you can be used for that as well. And all of this is in real time. Another application is surveillance. Alright? For instance, here the operator just uses a mouse to place virtual cameras at places where he or she wants, and all of this is in real time. Okay, I want a virtual camera here, one here, one here, one here, one here, all of it in real time by just moving a mouse, and you can see physically realistic video. In fact, just like that fairy tale, right? Mirror, mirror on the wall, or in this case, it's not the wall but the ceiling. Who's the naughtiest of them all? Yeah, you can find out here, pretty easy. Okay, now come to the last part of new sensors, which is, this is an image that's taken by an ordinary camera. As you can see, things which are at about 4 feet from the camera in this case are perfectly focused. Things that are closer to that and things that are farther away are not that well focused. Okay. How nice would it be if every pixel in this image were perfectly focused? Have a look at this. जो पास है वो भी focused है, जो दूर है वो भी focused है. Okay, this also turns out it's a pretty interesting way to do it. In this case, this is again high school math. That's one of the nice things about this. See, if you had an object that was straight, or rather everything on one line, a perfectly focused image of all points on this line has to be given by this image. It's just 10 standard trigonometry. You can easily prove it. Therefore, this is basically looking at the world in cross section. Now suppose I took many such cross sections. Okay? Basically I rotated the image plane. Suppose I had a little motor fitted here on the image plane and I rotated it. So at each point there would be some plane in the world, the pixels on which would be perfectly focused. It's possible to find out whether a pixel is perfectly focused or not. See, all are automatic cameras. Most of them have an autofocus mechanism. How does it work? It's no magic. We'll come to that as well. So if autofocusing is possible, it's possible to find out perfectly focused pixels. Okay? So these we can cut out and paste together to get a perfectly focused image. That's it. Well, this cannot be done in real time, because you'll need to turn the image plane. But the effect is fabulous. So these are some of the developments in the 90s, for instance, which have given us new sensors out of existing cameras. Right? You can do lots more with them.